Today I will devote the lectures on the actual examples of lasers. Okay. So, real laser systems basically. So, I will start off with the gas lasers. If you recollect in my initial slides, initial lectures, I had spoken about the various kinds of lasers that are possible. So, there I had discussed gas lasers, solid state lasers, fiber lasers and so on. So, today I will start off with gas lasers because in gas lasers, though ruby laser is a solid state laser and it was one of the first ones to be invented, but I will start with gas lasers because it will give you an idea of the energy level diagrams that are possible. They are sharp energy level diagrams, and then you can relate these energy level diagrams to the solid state kind of laser. So, let me start off with a helium neon laser, HENE laser, which is available in almost all lab. You may have seen it also in all labs. So, it looks something externally, of course, it looks something like this box here. Can't see anything, it's just a helium neon laser, and it has a power of 2 milliwatts, and sometimes it goes up to around 4 milliwatts. And it's used in the laser for alignment systems of other optical systems. It's a good alignment system because see, the output of this laser, it's a sharp beam, a red beam like this, just like an arrow it is going through. So, it's straight and a non-divergent, which is a property of all lasers, very low divergence, and it moves in a straight line. So, it is very good for alignment systems in a laboratory. Though helium neon lasers are used in holography and many other applications, which probably I will talk about much later. But at this moment I want to talk about the lasers so that you understand what 3 level or 4 level systems are like, or what is broadening, which you have already understood in the previous lasers, and now you are just seeing an application of all that in actual lasers. Okay. So, this is a box. Now, I really want to know what's inside this box. Okay, it's giving a red light. I'll give you the exact wavelength you will come across of this light. But here, this is what, it's a schematic diagram of the helium neon laser, but this is what it looks like inside this box. Okay. So, what do I have here? I have a tube, a glass tube like this. Okay. This is a glass tube, and you have a narrower portion of the tube which is shown here in the red line. So, it's a gas inside this. So, you have helium neon gas which is filled in this tube, and a part of that helium neon gas of course goes into a narrower section of this tube. And then how do I excite the helium neon atoms? Okay. And in order to excite, I need to give this voltage here. Okay. So, it's like a discharge, there is a discharge inside this gas because of this application of voltage here. This is the cathode, this is the anode, okay, and you have this medium here. And these two are the mirrors here, high reflector and output coupler. These two are the mirrors, like I have told you before, in any resonator you need 2 mirrors. Okay. Here it seems to be plain, but it perhaps is not. One may be a slightly curved concave type and one may be a plane type, so that it falls within the stability diagram, as you recollect in my previous lecture. Here I just want to clarify this output coupler. You are coming across this name for the first time. It is also a mirror, but then it has the reflectivity is not 100%. So, in case of this mirror, the reflectivity is 100%. So, whatever light comes here, it is reflected back. But in this case, because you need some part of that light to come out, I mean to be useful. So, you make that reflectivity say around 99% or 98%, depending on the amount of laser power or laser output that you require. You can have it from 98% or 99%. So, that part of the light is coming out, and the rest of it is again traveling back and forth between these two mirrors. Okay. So, this is the construction of a helium neon laser, and you get this output light here, which is a red light. Okay. Now, what do I want to show you the energy level diagram of a helium neon active medium. Basically, it is filled with helium neon atoms, and I want to show you how it can be excited, the helium and the neon, how it can be excited. So, generally what happens is helium is excited by this discharge. When there is a discharge, you have a lot of high energy electrons moving around within the cavity, and some of the helium atoms collide with these electrons, and the energy is transferred to these helium atoms. Okay. So, once this energy of these electrons, high energy electrons, is transferred to these helium atoms, it goes up to these two levels, 2s10, 2s20. Okay, these are actually spectroscopic terms for these levels. So, the helium atom is excited by the electron collision, as it is written here. So, it goes up to this level and also to this level. Okay. Now, the actual lasing action is happening in the neon atoms, okay, not in the helium atoms. Helium atom is just for this excitation process, because this is a very efficient process. Okay. And now the neon, this is the ground state, neon atoms, you want the neon at this level to be populated. Okay. The whole idea of getting this excitation done is to get finally a population inversion in the neon atoms, which are the lasing atoms, and once you get population inversion there, so you will get lasing action. Okay. Now, how do I fulfill this condition of population inversion in neon? So, neon has a energy level 5s. Again, these are spectroscopic terms, you can just look it up and see what exactly they are. But again, these are the states, 5s and 4s states. We want to populate these levels. So, now the neon collides with the helium, and this transfers its energy to these levels. Okay. Basically, it transfers its energy to the neon atoms, and they get excited to these levels. So, that is how the population of these levels keep increasing. So, from the ground level, the helium excites to the higher level due to electron collision, and then it transfers its energy to these levels, which are actually very close energy levels. The energy value of this and this is not very different. So, it is very easy to transfer the energy to the neon atoms and populate these energy levels. Okay. So, now this is populated, this is populated. Okay. The lasing action is taking place, the specific red line of the helium neon laser is because this is the lasing action that is taking place. So, the atoms are tumbling down from 5s to this 3p here. Okay. This is another level of a neon atom, and it is sort of empty now. So, there is obviously a population difference between this and this. All the ground state things have gone up to this 5s. So, here you have a 3p level and it is falling down. So, 632.8 nanometer is the exact wavelength of this red light. Okay. But at the same time, From 5s it can even go to 4p. 4p is also kind of empty. This is more populated. You do have a population inversion between these two levels, and this is 3.39 micrometer, and one more possibility is from 4s to 3p. So, you have three possibilities from 5s to 3p, or from so from 5s to 3p, or from 4s to 3p. So, three lines are possible. 1.15 micrometer is in the near infrared range, and 3.39 micrometer is also in the infrared range. But most of the time we think of helium neon laser as a red light instrument. Okay? So, red laser light. So, now this is the most efficient, that is why this is happening. And then now this should also be depopulated. So, there is a fast radiative transition from 3p to 3s, and then diffusion to the walls brings the atoms back to the ground level. Okay, diffusion to these walls. And it has been found that if these walls are very narrow and very close to the actual helium neon gas, then this efficiency is very good. And with this efficiency going up, this diffusion to the walls, your population inversion becomes better and better, and your red light emission is again definitely more efficient. Now, the point to note here is that helium neon is a 4-level system. Just recollect a little bit of the previous lectures, just revise there, and the 3-level, 4-level and the 2-level systems. So, the 4-level system was kind of, we had seen earlier, kind of efficient, So, helium neon is a 4-level system. Which are the 4 levels? This is 1, this is 2, this is 3, and this is 4. Okay? This is the ground, 1, 2, 3 and 4. Okay? Because it's a 4-level system basically. Okay? Now, helium neon lasers are available nowadays in many other colors other than red. How does that happen? Initially, the red line was discovered, was invented, but later on people found that you can get some other lines also. Okay. So, which part of the energy level diagram will give me the other colored lights? Okay. So, this is the other colors of helium neon laser. So, again I go back to this 5s level. This is excitation from the ground level of the helium, and this is the neon. So, this is a 5s level. So, if you see the 5s, there are kind of 2 levels possible, which I had not shown in the previous one. Okay. So, I just shown it as one line. Okay. But if you look a bit more closely, you will find that there are 2 lines. Okay. That is what people found. There are 2 in this 2 sharp lines in this in this 5s level. Okay. And then even the 4s level, you have these 2 lines when you look a bit more closely. And the 4p and the 3p are kindly sort of broadened. So, there are a few more lines, not just one line. Here also there are few more lines, and that increases the possibility of different kind of lasing action. So, this principal red line is from this upper level to say one of the levels of 3p. But then from the upper level, it can also fall down to one of the lower levels of 3p, and that gives you the green light, which is 543 nanometer. Similarly, from the 4s level there are two more lines possible. So, you have a yellowish kind of line and a blue kind of line shown here, and the rest of it is of course the same. It relaxes back here and then relaxes back to the ground level. So, here is all the population that is occurring. Okay. So, because of this fine tuning of these lines, finer details of these lines, you get a few more lines in these two levels. So, more lasing action is possible. So, you have a red and the yellow line. Okay. I am talking other than the red and the yellow line, 594 nanometers. The orange line is 612 nanometers, and near infrared is 1.1, and it is a common wavelength. Most common is of course 632, which is the red line. The letters have just got a bit jumbled here, and the green is 543 nanometer. Okay. So, you have all these colors from green, slightly blue, orange, red, okay, possible for a helium neon laser. Let me just go back to the previous slide. Okay. So, now how do I prevent the other lines from becoming the dominant line? You know, there is green, there is blue, there is red, say these three. How do I make only the red laze? Red has the maximum gain, so it is most likely to raise. But how do I make say the green line laze? So, I need a helium neon laser which is giving out a green light and there is no red light. One way of doing it is you coat these mirrors here, the mirror here, the output coupler here and the high reflectivity mirror here. You coat them in such a way that give it a good coating so that only the green light is getting reflected back. Okay. And it is giving a very low reflection to the red light. Once you do that, slowly over a period of a number of oscillations between these two reflectors, the green light will dominate. Okay. So, all you are doing is changing the reflectivity of the two end mirrors, and that is one way of suppressing the red and giving way to the green to laze more and more. Okay. So, these are some of the techniques that are used anyway. So, that is something about the helium neon laser. Let me now talk about another gas laser, a very important gas laser, which is the carbon dioxide laser. Now, the carbon dioxide laser lasers in the infrared region. Okay. So, basically you can't see it, you just can't see it. 10.6 micrometer, it is in the infrared region. So, it is difficult to see the laser line, like the red line you can see it. But here I give a picture, a picture of a laboratory where a carbon dioxide laser with kilowatt power. Okay. In case of the helium neon, it was around 2 milliwatt to 4 milliwatt. Here I am talking in terms of carbon dioxide lasers can laze in the kilowatt power range. So, in this picture I have a continuous wave. Now, you will come across this term more often, continuous wave. That means it is not a pulsed laser, it is a continuous wave CO2 laser. And here what I show is a target on which the beam of laser light is falling. Okay, you can't see the beam because it's in the infrared, but when it falls on the target, it can burn it, and that's what it's burst into flames here. All you can see in the carbon dioxide laser is a pinkish glow here. So, again the pinkish glow is because it is a glow discharge within a glass tube which is filled with carbon dioxide. Now we should know what is inside this carbon dioxide laser. Okay. So, what is inside this is the following. Okay, this is just like I have shown before, this is the schematic diagram of a carbon dioxide laser. This is, say, a glass tube in which the gas is filled, and these are the anode and the cathode, and you give an electrical impulse and you have a glow discharge within this. Okay, glow discharge, and it starts glowing in this color, this pink color. Okay. But that is not the lasing action, that is just the glow discharge. So, here you have this, and what you fill inside this is you fill nitrogen, helium and CO2. Okay. So, what you have is N2, helium and CO2. Okay. So, CO2 is where the lasing action is taking place. So, we will be interested in all the energy levels of the CO2, but the nitrogen helps to get a population inversion in CO2. Okay. And what does the helium do? The helium is kind of a cooling effect. It transfers the lower energy level population to the ground level. Okay. So, you have 3 gases and in different proportions. It could be N2, helium, CO2 could be 1:1:4, or it could be 2:1:3, you know, CO2 being the highest. But depending on your use and the kind of application you want, you can keep on changing this. But without all these three gases, the carbon dioxide laser will not work. So, you need to put in all these 3 gases inside here. And in a CW laser with a kilowatt power level, you need some cooling systems. So, here what I show in blue is actually a water jacket. So, this inside part is a glass tube, and on top of that you have another glass tube sort of thing, a jacket where there is flowing water. Okay. There is flowing water, and then you have some inputs for maybe through this or through some other inlet you put in helium, nitrogen and CO2. It is a continuous flow of this gas, continuous flow of nitrogen, helium and CO2. And again here you have the 2 mirrors which forms the resonator, this mirror and this mirror. So, you can see one is slightly curved and one is a plane mirror. It falls within the stability of any resonator, stability diagram, it falls within that. So, this is what you find there. So, now I must talk about the what exactly the CO2 is doing, what are the modes of CO2. Okay. So, here in this diagram I just point out all the modes in a CO2. So, the center one is the green one is carbon, and on either side you have oxygen, carbon, and on either side you have oxygen. Now, there are 2-3 modes in which this carbon dioxide molecule acts. Okay. So, you think of this bond between carbon and oxygen, this bond between carbon and oxygen as, say, a spring. Okay. So, anyway, this is a bond, okay, here, and this is also a bond here. Okay. So, you find them to be some kind of spring action, it is just an animated way of showing. So, how can these modes move? So, these 2 oxygens can come closer to carbon dioxide, move, come closer, move, come closer, move. This is one mode of action, okay, in a carbon dioxide molecule. When they have energy, basically when it is in a excited mode, it starts moving in this. It gets energy from the discharge and it starts moving in this way. Another mode of movement is the oxygen here. The oxygen here may go down, oxygen molecule. Sorry, this is carbon dioxide molecule will go down and these two oxygen molecules go up. Okay. The oxygen molecule is going up and the CO2 molecule is going down. Okay. So, this is called the bending mode. So, basically bending mode because the bond in between is bending at an angle and it is coming down, oxygen is going up in one direction and the carbon dioxide is moving in, carbon is moving in the other direction. So, you have an angle in that bond. So, that is why it is called the bending mode, and this is called symmetric stretch construction. Okay. It is symmetric stretch because both the oxygens are symmetrically moving towards the carbon is stationary and it is moving out. And here it is the asymmetric stretch. Okay. This is asymmetric stretch because one oxygen is moving towards the carbon and one oxygen is moving away from the carbon. So, it is asymmetric. So, this is again another stretch mode. So, when the carbon dioxide gains energy, these are the three ways in which it starts moving. Okay. And that is what gives you the energy levels. Okay. So, in my next lecture I will continue with this and show you the energy level diagram.